Okay, so line integrals. Uh, there are two types of line integrals, scalar line integrals and vector line integrals. So starting with scalar line integrals here, um, they are expressions of this form. Notice you have a differential that is ds there. And I'm going to try to explain how conceptually this notion is built up. So you start with a curve C, and you subdivide it into portions, and you within each portion you pick a representative, these pi's, which would give you the value on the segment, and then you would sum up. You'd construct a Riemann sum out of this by using the value of the function at the point pi as being the height of the Riemann sum, and then the length of the arc, or the subdivided curve. The length of that subdivision is going to be the delta s, and then you sum up over all pieces. And then to turn this into an integral, you take the limit as your subdivisions, the size of your subdivisions go to 0, which means that the n would go to infinity. So this limit of this sum ends up being the definition for how you create the scalar line integral. So this is similar to how the notion of integral was defined. It was also defined as a Riemann sum. And, well, we're going to want to not use this definition in practice, but this is where it's coming from, kind of just conceptually. Before I kind of introduce that more useful calculative approach, we have this property. So if you're taking the scalar line integral of the function 1, that is simply going to be the length of the curve, which kind of fits into place with all the other integrals of the function 1 that we've seen. So when you integrate the function 1 over a two-dimensional region, that measures area. When you integrate it over a three-dimensional region, that gives you volume. And here, where we integrate it over a one-dimensional region, that gives you length, which is kind of as expected. I think that usually when the formula for arc length is taught, that's kind of tied into this. We'll see shortly that the ds is actually an expression that is the thing that you would have for the arc length. It's part of the arc length formula. Okay. Anyway, so where are we? Yeah, okay, so we're going to start by now introducing a parameterization on our curve. So we introduce this parameterization r of t, where t goes from a to b. And passing that idea through this construction, right, where we have these subdivided arcs, we would then have time values that correspond to chopping the curve into these pieces. You'd have times for each of those kinds of subdivisions, and then you end up picking a t sub I star that corresponds to that representative, the pi, that we chose before. So the point is that the expression that we started out with can end up being approximated by a version that uses the parameterization. And then the parameterization is easier to work with in practice, like through calc. Once we have a parameterization, it's more easy to calculate things rather than having to deal with a limit of an infinite sum. Okay, so you can see that here we end up plugging in at the point that corresponds to this f of pi. And then this part, some things are being stated here about how this quantity approximates the length, right? So that's more or less here. The idea is that as these pieces get arbitrarily small, this change is more or less constant, and so this integral will end up corresponding to the length of the subinterval, which is going to be equal to delta s. So that's how this delta s ends up corresponding to this expression here. Okay. And then when you take this sum and you take the limit as n goes to infinity, then the sum turns into an integral, it turns into this integral. And so this integral is the expression you use for computing scalar line integrals, which is here, right? You can see that this is the expression there. So if you have a parameterization t running from a to b, or r of t running from a to b, then the way you compute a scalar line integral in practice is that you plug your parameterization into the function, and you also need to take the derivative of the parameterization and take the magnitude. And then you take the integral of the product. Yeah. And yeah, so here I'm saying, yeah, that delta s is supposed to make you think of arc length, and when you you can think of ds as being this quantity. So being a symbolic equation means that we're just think of it as like this is a symbol replacement. It just this ds kind of expands into this. Okay. And yeah, if you have this quantity, this you should remember from as being like arc length formula. I think from like Calc 2. Okay. Right. So now here's an example computing scalar line integral. I think that this didn't show up in your homework, but you should have been assigned a problem on it, because it's very common that you have to compute scalar line integrals as well as vector line integrals. So let's go through this example. So we have this function, and we have this parameterization. So the first thing I do is I take the derivative of the parameterization, then I take the magnitude, right, which gives me that. And we're trying to set up this, right? So this is the expression for the scalar line integral. F is this inner function there. And we're going to want to write it in this format using the parameterization so that we can actually compute it. So we've computed this part from this. Next we need to compute this. We need to plug the parameterization into the function. So the parameterization, I copy it down here, and then we just plug that into the function, which is above. So plugging that in, we get this. So that gives me this line now. And then from there, what we do is we just integrate. I think that's pretty clear. Yeah. And then we evaluate. And if you evaluate, you get that. So that's how you compute a scalar line integral. Okay. Now some applications of scalar line integrals. So, well, so in general, I guess the physical notion is that your function inside can be thought of as some form of density, and so then the integral of some kind of density function ends up measuring the total quantity of whatever the density is measuring. So if the function inside, I'm labeling it rho to make it look like a density. If this is the mass density of a wire, so think of the curve C as being a wire, and rho is its density at some position x, y, z, then this integral will measure the total mass of the wire. And if rho was instead, say, charge density, then the integral, then this scalar line integral would measure the total charge on the path, or on the wire. Okay. Right, now for vector line integrals. So there's an important difference between vector and scalar line integrals, and that is that the vector line integral depends on direction. So yeah, the vector line integral depends on the direction along the curve. So that is important. So in order to talk about the direction, we introduce the terminology of an oriented curve. So a curve is oriented if it has an orientation, that is a prescribed direction that you would traverse the curve in. And so if your parameterization ends up matching up with this curve's orientation, then we call that traversing it in the positive direction. Whereas if we oppose the curve's orientation, then we're going in the negative direction. Okay. So there's that. And then, yes, this term closed. So this will show up more later on using this word closed. But so there's a kind of technical way of describing it, which is that you end up having a parameterization with endpoints A and B that are like the ends of the parameterization, but then you also have that plugging into the parameterization at A and B ends up being the same point. That's a very mathematical way of describing it. The more layman way of describing it is just saying that the curve is a loop. So the two ends meet up, they join together, and they form a loop. Yeah. Okay. And you can see pictures of this. So this arrow here would be what we're calling the orientation, and this is this is pointing in the direction. Is it pointing in the direction? It's not. It doesn't have to be pointing in this way. The way that this is drawn, it looks like this is actually the derivative. It looks like this is where the parameterization is changing, but it doesn't have to be. It could just be like this way, and that would still be acceptable. I think, unless I'm thinking of something else. I might be plugging into the vector field instead. No, okay, based on this picture, I am starting to see, so I believe that that's what's going on. So you plug in R of t, that's going to be the point. R prime is going to be the vector in pink. So that's what this figure is saying. Yeah, so R of t itself, I mean, it is a vector, but it's a vector starting at the origin and going to that point, which we then associate with a point in space. So R of t is actually this point in space. And R prime is the vector that's tangent to the curve. Okay, that makes more sense. Yeah, and so yeah, again, this arrow is the orientation. Same with this. I think that's enough on that topic. Right. The line integral. So this is the definition of a vector line integral. So the idea is that what you want to capture is how much of your vector field is in the direction of your curve. You're trying to capture that commonality. And so the way you do that is you end up taking a dot product with the tangent vector to the curve. I should have a picture of that below. Yeah. So you've got some random vector field that is in green, and you have a curve, a line that you're traversing, and then along that line you have, a tangent vector. And so in blue, these are the parts of the vector field that are actually on the curve itself. Okay, so this f is part of the vector field, but it's the specific vector that you get at this point, which is on the curve. So to measure how much in the direction of our curve this vector contributes, we take the dot product of f with t, which is this diagram, that's going to capture how much in the direction of the curve. And then we sum up along all such points on the curve, which turns into an integral. And so from this definition, you can already see that that's why the vector line integral depends on the orientation of the curve and the parameterization. So if you're going in the same direction versus like in the opposite direction, you will introduce a negative, because in this formula, the direction of t depends on the parameterization. So if we reverse the orientation, we will end up reversing the direction of t, and that's going to introduce a negative into the dot product. So that's a property that I will list later on, but that's something that you can already see from here. Okay. Right, and now so the way that we set up a parameterization typically is we want the parameterization to be in the same direction as the orientation that we put on the curve. That's the standard way we would parameterize a curve, is to follow the orientation of it. Okay, so that's what that's saying there. And I'm writing down a justification for why this quantity ends up equaling this quantity, so that we can then use this formula instead of well, I mean this formula still looks fine, but in practice, like, yeah, you'd end up using the parameterization. So just noticing that this unit tangent vector is this, right? You take the derivative of your parameterization and then you normalize it, divide by its magnitude. So that gives you that, and then we start inserting the parameterization here. The ds is this norm of r prime times dt that was shown above. That's kind of just a definition. And you can see that these two parts cancel, which then gives you this final expression. And so we're justified in saying that this is equal to this. And so this is a useful formula to use. I would say that these definitions are probably going to be on the formula sheet for the test. But I mean, if you compute enough of these things, you'll end up memorizing this formula and the same one for the scalar integral, where instead of this, you end up having the magnitude. I guess I should emphasize, this is a dot product, right? So you see that f of r of t is a vector here, and this is a vector here. So this is a dot product. Whereas with the scalar line integral, this ends up being a number times a number, right? So that's why we have a magnitude here, and turning this into a number, and f of r of t is, you're evaluating a scalar function at a point, so that ends up being a scalar, a number, and just scalar multiply. So that's the important difference to be aware of. Okay, and now I'm starting to set up a justification for something, for a different notation for vector line integrals, which is, I find it a little bit strange, but it's a fairly standard thing to have. So, okay, first, yeah, so dr, this quantity dr, maybe I'll circle that. So dr can be thought of as this infinitesimal kind of direction, I want to say. So it's a vector differential. And symbolically, we can rewrite dr as being r prime times dt, right? Which is pretty much what happened up here. Okay. And so, well, this r prime is this quantity. So we have this kind of symbolic equivalence there. Okay. Right, now here's an example of computing a vector line integral. So we have this vector field, and we are told that the curve C is parameterized in this way. And you want to compute this guy. So to compute this guy, we need to take the derivative, and we need to plug R into the vector field. Right, so first I just copy this down. Now when we plug it into the vector field, so I'm matching things up. So Z ends up taking the Z component of R, right? And then Y squared takes the Y component of R, which is going to be that. And then X takes the X component of R. Okay, so that's F of R. And then we also need R prime, so I just take the derivative of R. Gives me that. And so the vector line integral, well, we use the formula, so it ends up being this, 0 and 2 coming from the bounds of the parameterization. And then we have all these quantities. We computed them beforehand, so we just pull them there. And then we take a dot product. Yeah, that should be pretty clear. There's a slight simplification because it's t squared plus 2t squared plus 2t, so we end up combining one of the terms. And then you integrate that guy. Oh, and I didn't write down the final answer here. Okay, I guess I... Well, so at 0, it's 0. No, it's not. Actually, it's not, is it? Because this is going to give you something. Alright, so that's a little bothersome. 1/3 e to the 6th plus 8 plus 4 minus 1/3 because of the e to the 0. Okay, so that's fine. That's going to be, I'll just combine this. So it's e to the 6th minus 1 plus 12. Alright. Fine. Okay. Right. Now here's this thing. So we have another standard notation for vector line integral, which looks kind of funny. So it's written like this. I don't know why this is used, honestly. It just seems weird to me. I'm still not used to it. But there's a bit of a justification for why this relates to this. And it's through just kind of messing around with the expression symbolically. If you think about dr as being a vector of differentials, like this, well, and if you have f have component functions f1, f2, f3, then this dot product, if you actually expand it out, ends up being this quantity, which is exactly that. So yes, you can really think of them, they are the same, you can reason about it like that, but I don't know, this thing just still looks funny to me. Another way of then thinking about calculating this using a parameterization, so if you have a parameterization r of t being with component functions x of t, y of t, and z of t, then dr will then be dx dt, dy dt, and dz dt. But now these guys are actually functions of t. And then you have this dt there. And then you're taking a dot product with f, and then you insert the parameterization in order to get this quantity, and so that gives you this kind of way of thinking about this notation for a vector line integral. Yeah. Okay. Right. So you have a problem that makes you try using this kind of notation, and it really is kind of just matching things up. So when I think about it, I just compute the dx and dy from from the parameterization. Dx and dy end up being r prime of your parameterization, and then the y and the 3 are the y is coming from the parameterization itself. Wait, there's a so the way that I think about this is that there's a vector field, but it's not shown. It ends up being the vector field 2y comma minus 3, right? It's not shown in here. Instead it's kind of been incorporated into the line integral itself, but it's there. So that's how we map it to the previous way of computing these vector line integrals. So, okay, well, r is given. This time theta is being used because this curve being described is actually an ellipse, so theta kind of makes sense instead of t. So, okay, we start with r of t as given, then r prime of theta. R prime of theta, we just calculate it, not too bad. And then we plug into this. Right, so theta goes from 0 to 2 pi, so we have that. And then 2y. So y comes from r. The y function, sorry. So it's this one, that goes there. And then dx. dx is this guy. Right. So it might be, it's kind of better to think of it like this. So you have x and y, and you have dx, and you have dy. That's how I think about it. So that's what you have there. Okay. So that's dy. This part is dx, and then minus 3, and then dy. So yeah, you can see that there. And then simplifying that, and then taking the integral, you end up with the final answer. Okay. These properties, they're useful to know about. They don't show up that much, but it's just kind of nice to know that these integrals have properties that you would more or less expect. So first of all, linearity, right? So the line integrals are linear. You can split it over addition, subtraction. You can pull scalars out of it. There should be a d there. That's a typo. D there and D there. Okay. And as I said kind of early on, orientation reversing. So if you flip the orientation of your curve, the line integral over the curve is, of the reversed curve is going to introduce a negative. So yeah, reversing the orientation of the curve introduces a negative to the line integral. Okay, and then additivity. So what that's saying is if you split a curve into different paths, I guess we could draw a picture of it. So all I need is a few points. So C1, C2, and C3. So so the whole path would be C. But we could, so the line integral over the whole thing is going to be the sum of the line integral over the parts. So C1 to C2. Oh, actually, the way that's labeled is not so good. I should call C1 and C2 should be the segments. These would be like P1, P2, P3 from the notation that defined these line integrals. So yeah, so the line integral over C1 plus the line integral over C2. The whole curve is the curve C. So yeah, that should be fairly intuitive. Okay, now for applications. All right, so the first application is that the line integral measures the work performed by the vector field. Okay, so this line integral measures work. And then here's an example. So if you're asked to calculate the work performed by a vector field in moving a particle along a given path under a force field that is given there, well, you go ahead and you compute the corresponding line integral for work, which is this. And so, as you know, you're going to end up needing to calculate f of r of t dot product with r prime of t. So you need each of these pieces. So f evaluated, well, plugging r of t into f, I guess I should say. You plug these into here, so you can see that x squared ends up being this t squared quantity squared, which is t to the fourth, minus z ends up being minus t, and then this minus y z to the negative first, that's minus t cubed and then divided by t, which gives you a minus t squared. R prime, you just take the derivative, that's pretty straightforward. Then you take a dot product, and that should be straightforward as well. You can see you get that. And so this is what you have to integrate from 1 to 2, and you can go ahead and compute that. That's just a polynomial. I didn't bother to write down the details of that. Should be fine. Okay. Another application is that there's a line integral that computes what's called the flux across a curve. And so the definition is different than how we defined the line integral originally. Instead of, so do I write it below? I forget if I do or not. Okay, so the typical line integral, it was defined as being f dot the tangent part ds over c. But instead, for flux, we're defining it as the normal component. Okay, so that's the difference. And so it's capturing kind of the orthogonal part to what we were considering before. It's capturing the other part of the vector field. When you dot product it with the normal vector, you are measuring how much contribution is given by the vector f. That is, instead of going in the direction of c, it's completely in the opposite way. It's perpendicular to c. So now the symbolic way of writing the normal vector is it's going to be a rotation, a right angle, 90-degree rotation from the tangent vector, which is this quantity. Although another way to think about it is that if you take this and you dot it with r prime, you end up getting 0. Right? So if you take this and you dot it with this, you end up getting the 0 vector. You see that the things cancel out. Okay. So yeah, so this is the definition of flux. It's defined in this way. We normalize it. I'm thinking, is it? Yeah, it is. It is necessary to normalize it here, but then we end up not needing it over here because this magnitude of n is equal to the magnitude of r, and you can see that because if you take the magnitude of this versus take the magnitude of that, you end up with the same expression. So this is the expression that you, why is it not drawing? This ends up being the expression that you use for computing flux. Whereas if you're just doing it abstractly, you'd represent it like this, but once you actually want to compute it, you impose a parameterization on your curve and you compute it in this way. And I guess this is a specific physical version of what I'm saying here about these fluxes. So if the vector field f was actually the field was measuring the velocity of the fluid, right? So a bunch of velocity vectors, then the flux is the amount of fluid that flows across the curve per unit time. Okay. Calculating flux. So just a concrete example, calculating things. So flux of this vector field across this given curve. This curve with a given parameterization. Well, yeah, it's the same kind of procedure. So looks like I typoed some more. That's like that. So the flux is calculated by this expression. Now in this problem, the notation got changed a little bit. So instead of F for the vector field, V was used because it's a vector field of velocity. So we have V instead of F, but otherwise it's all very much the same. You need to... So R prime is computed first because we need that to calculate N. Right, so starting with, once you calculate R prime, then you swap the two and you introduce a negative for the Y per the definition of N there. So you do that to get N, and then you also need to plug the parameterization into the vector field, which will give you this and simplify, and then you take the dot product of these two vector functions, which then gives you this quantity. And so the flux is measured by the integral over this quantity, which, well, it's a calculation if you're going to do it. Actually, yeah, no, I think it is a calculation. I was thinking of, sometimes the shortcuts can be done if this is like a 0 to 2 pi, specifically like, I think it's that products of sine and cosine, if they're of the first power, they will cancel and give 0. It's because sine and cosine are orthogonal to each other. But here we don't have that. They actually all contribute, and yeah. Okay, so I guess that's it.